All right, so let's get through first the subtasks number 2. So this subtask 2, it was about the single events shown here. So first of all, I asked you to get familiarized with this localization application, which we did go through last time, and to see what is doing and what input files do you need, and some general functionality of that. Then I was asked you to select one of the episodes that contains all the necessary input files for this, and then the same thing for the spectral analysis. And then I asked to do some basic use of the applications. And for the localization, I asked you first to use only portion of the stations what are for the selected event, and then increase the number of used stations and see that how does it apply in the localization. And the same thing for the spectral analysis, just using a couple of well, it doesn't read here, but in the end you can do this for just a single phase or multiple stations, but we will see. Furthermore, I gave you this one application that we didn't go through last time, this focal mechanism application called FOCI, which describe the focal mechanism of the particular event. But let's start with the localization and spectral first. So since I have gone quite many times through the basic things just of getting the episodes, so I'm just going those quite fast. Since this is recorded, you can look them afterwards if you're trying to mime it now. So first of all, let's go to the applications and look the localization. And it is this one. So this uses this tremolo localization software, and the main task is just to locate the hypocentral location using the probabilistic inverse theory approach. And to use this, we need seed waveform, except that was a mini seed format, catalog, seismic event ID file, then multi-seismogram peaks for the first arrival for the P wave and the velocity model. And I'm just adding this to the here in the subset 2 folder I have created. And here we have I have already placed it here Pyhäsalmi and USCB files. So if we look at the localization first, we need the mini seed, network, catalog, and the velocity model at minimum. And I have already retrieved them in the from the Pyhäsalmi mine. So I selected Pyhäsalmi myself. You have maybe used another episode, which is totally okay, because now the important thing is just to go through these steps. So let's take this from here. So first of all, let's go get those obvious ones. The network, as well the velocity model. But we see that we can also put the mini seed and the catalog are needed, but I ask you to filter the catalog to contain just the largest one. So we can filter that just using the catalog in the application filtering here. And let's find the local magnitude here. Selecting range 2.3 is the largest one. was 2.1 anyway. So I just select the range from 1 to 2.3 magnitude. So this should narrow considerably the amount of events in the output catalog. So there's only 7 events in Pyhäsalmi mine that are above local magnitude of 1. Now we can see from this workspace tree that the catalog is here. So we can use now this new catalog to retrieve one of the seismic signals. And that was done using the signal download tool. And since we use that catalog, it automatically put it as an input file. And then we will just select the events from the catalog. And here are the 7 events in the catalog. So we can go and look what is the largest one. Last one is this 2.2. I'm going to select, for instance, this 1.3 over there and click OK. And in Pyhäsalmi mine, we actually have both the seed signal and the mini seed signal. So in this case, I'm just going to retrieve the mini seed signal. And it contains the event file as well the mini seed. Okay, good. Now we can go back to the localization application and go retrieve the filtered catalog. This could be renamed to be more descriptive, but I'm just using now this one, the default naming. Okay, and then the mini seed file. This one. Right. And now that we inputted the mini seed, it automatically loads all the traces associated with this event. And then when we go here, we need to have the event coordinates, the original ones, and we can load them from that event file, what we had during the signal download.
Sorry, Jenny, can you go back a little bit on top of where you uploaded the 4 files?
All right.
On top, yeah. So
yeah.
That one, correct? The network Can I know where did you obtain that network?
That one.
Yeah.
This one can be obtained from the episode. And at the episode, you need to take the Pyhäsalmi mine seismic network. There's also this national one. Go through that. So Pyhäsalmi mine. This is the Pyhäsalmi mine episode page. So over here, the network. And from there, you can take this network. The other one is this macro events network, which is the national network of Finland, at least portion of it. Yeah, so the original localization tool, it says that it needs this seed signal, which automatically does have this network information, but afterwards they have split them to be in the mini seed waveform and the network separately for some reason. And the event coordinates was this event file was generated in the same time when the signal was retrieved. This JSON file, and it just gets the coordinates. Okay, so This actually is, I think this is actually quite tricky event. I think this is quite far away from the mine actually, at least localized. But nevertheless, we can look that. Yes, this is quite much more. This is not the local one. So you can see that there's quite many, well, not that many seconds before this is more like those earthquake observations seen from a macro station. Anyway, we can see that here is the first arrival, and I think S wave is somewhere, probably this one actually already, and these are the surface waves. But now we are doing the localization. We are only interested in the first arrival of the B wave, so we can zoom in and clicking the time where we think that the B wave has arrived, and it's around here. As you can see that this is quite discrete to do the sample rate, so I'm just taking that one. And in localization, if we go down here, we need at least 3 of the peaks over here. So let's take the minimum first. Next station over here. This is a little bit more noisy, but I think it's here. And let's take that one. Less noisy. I think it's that one. This is quite small. Now we have taken the first arrival from the 3 stations, and that is the minimum. And then I'm just using these default settings here, and let's run. While it's running and calculating this, we can go through what these are. Okay, already did it. The variance of x, y, and z, it gives for the solution some mathematical inputs where to start for the processing for the inversion of into this demo block software. So larger the follower here is, it kind of gives more opportunities to starting the localization. It can be a good thing, especially if there is not too many of stations. Then there are some norms for the distribution, and a posteriori PDF norm, which is this probability density function. We don't have to go on that, so we can just do this G. You can look for this from the user guide, what they mean. But I think in this course we can just handle with this basic default settings on that one. Then maybe most crucial what you can affect here is the minimum jet value and the maximum jet value in meters, from 0 to 5 kilometers, and x, y, z steps. When it's doing the iteration and the localization, when you're running this, it kind of gives the location to change this much between the iterations. So the larger it is, the more faster the localization is, but it can be that it doesn't get in the very detailed location. If you put this as much smaller, it takes a lot longer time, but the result would be better. Of course, sometimes if there's too few stations, it may be that it can't resolve the localization at all. So that was a very short introduction on these properties and parameters on this localization. Now we can go and look the results. Okay, so here are the 3 stations that we used to pick, and here are this is the location of the seismic event in the catalog. So as you can see, it's quite far away from these stations. These stations are something like 100 meters apart. And so this means that the event is located very far from the Pyhäsalmi mine. So this event actually is not from the Pyhäsalmi mine. It comes from somewhere else, but still it has been recognized as a using this network. Then we can have seen here the average solution and maximum likelihood solution and the original event. So this was our first, and it's quite not very good localization, because it's almost half kilometer distance on the error margins. And if we think about it, that this event is only a few kilometers away, so that is quite high percentage of error. Then here is the relocalized events depth, which is quite nice. The depth is more or less correct. Then I was asked you to increase the number for the localization. I doubt that this will increase this super much, because the event is outside of our grid. But let's anyway do it.
Sorry, a question.
Yeah.
How do you close the signal? Like
the tune.
Yeah, close it. Not like close
That one.
Oh, okay, that.
Yeah.
There,
Yeah.
That, I always got them open. But
yeah, it kind of gives that zoom in. So I will now pick the B away from all the stations. That's odd. This is other way around. And let's take the last one still. I think it's that one.
And for this location case, with just the keyway is enough.
It is enough in this case. Of course, we can't even use actually S-Wave in this application. We could use, it can't be used the S-Wave, of course, but in Pyhäsalmi mine and this application, we only can use the B-Wave. It's a rather simple algorithm. So when all of these have been picked, we can run this again. At this time, of course, we could copy these ones for comparison. Another way, not just copying it like that, would be that we would change the name from here, from the output file. But then we just run it again. And still it didn't take too much time. Okay, as you can see that from the localization point of view, it didn't increase a lot. That the location is exactly the same, a little bit changed in the longitude, but not too much. And the reason for this is that this event is outside of our seismic grid. So I kind of take a poor selection of selecting the only event that is actually localized outside of the grid. But it's more or less there. These two, they are practically in the same spot. And the depth is almost the same. And difference is also that it may be that the original location is using somehow in some degree the S-Wave as well, because it's different. It is a different software that has been used, but the scale and the location is more or less the same. So this is more or less mission accomplished, and our B wave selections are more or less the same, the way they should be. I can go through quickly another one. So we are probably going to use this anyway in the practice work. So let's take, for instance, that one. So I'm just retrieving a new signal. And I'm putting that, as you can see, that I use the same signal download tool. So it deleted the previous one. So this says that it cannot find it anymore. So I'm just taking that new one. And it loads the signals. Meanwhile, I'm going to get that original location from the filtered catalog. It was that one. And you can see that there's now the signals are much more compact because the source is much closer. And in this case, it's better to zoom a little bit the signal to see that whether this is the first arrival of the B wave, and it is. Selecting like that. Again, zoom. Yeah, there it is. Yet another. Oops. Now you can see that there's, if I wouldn't zoom this too much, I would say it is that one. And but it actually can be that one also. But there's not too many samples here, so I'm just taking the big value over here. Sometimes it's better to take the more clearer signal than the small one. Then yet another. I think it's that one. Right, now picked 4 stations, so I just go and run the software. So here we can see that now the original event has been within the seismic network, and this is our relocated maximum likelihood solution as well. The average solutions, they are right top of each other. But there's a large difference between this localization and the original one in the terms of depth. That's 200 meters, which is quite much. If we think about it, just a small scale. So in order to improve this, we should use more stations. And now that this event has been inside the mine, we can see that quite many more stations has observed this. And you can see that there's a quite time delay, at least this relative time delay between stations. And these ones, which are the earliest ones, they actually are quite close to that seismic event, like 1, but 19 and 16 are more far away. So let's take a couple more. So zooming in and taking the B wave. First arrival, let's take that one. Still zooming that one. zoom in and we can a little bit further zoom so we can get the point more exact here. And one more. It's that one. Yeah. And then again, just one. Okay, now you can see that it's outside of the grid. So most probably I've taken wrong B wave in some of these. It might be that some of these stations are not in line. Yeah, I think it's actually that one is the 1 and 3 are maybe the problem here. Or actually maybe that one. Yeah, I think it's quite clear though. So this means that sometimes we can have multiple signals at the same time. So it's better to delete some of those. That is also quite late. And I know that this station PS30 is actually on the surface. So it's quite far away from our seismic event. So let's delete that also. So sometimes, especially if we think about our network, and it should be a very good idea to try different stations and peaks and look at how the localization is developing. Okay, now we're back here. And in the Pyhäsalmi mine episode, if we would go look the catalog itself, let's look the catalog at the time. That one. There is actually a parameter called used station locations and unused station locations. And we can go and look that from the catalog preview more in detail. So it was the second, that one. So for the original localization, these stations has been used 10, 21, 30, 20, 22, and so on. But the 28, 29, 25, 27, 26, these are for sure at the surface. They have been dropped out of the analysis. And also they have used also the S and P wave.
So we should not use the one that you use?
This is what they have used when they have made the original localization by the EMS, which is the networks supporting and they're handling the events. You can use those, of course, and test those in the Pyhäsalmi mine because it will give, but because the Pyhäsalmi mine's seismic velocity structure, it's quite simple. But the mine itself is not very simple. If we think about it, that we have surface geophones, I think it's best to go look at that picture over here. If we think about that one, that we have some stations at the surface, and then we have the seismic event occurring here at the bottom, and most of the seismic sensors are around this deep ore body. So we can see that this is not very homogeneous, this region over here. So those very far away of stations can distort the localization quite significantly. This applies also for the spectral analysis. because there might be some distortions in the when the signal and the waves are propagating through this very region over here, because it has a lot of tunnels and lagoons and different kind of, it's not homogeneous in the terms of intact rock. Here we have more stations, and although there's tunnels, of course, and there is ore and side rock, it's the same for all stations, and there is not this big gap over here. And usually applications are trying to handle everything like equal, and if there's something which are a little bit distorted, it can affect on the localization, and I think that happened on that localization. And also there's this that the big events are more difficult than the smaller ones, because they're usually they are larger in the way that the rock mass is breaking a lot more. So there's a lot of different kinds of signals coming from that. So sometimes they are most challenging ones to analyze. But the location is still there, and it can be a little bit different. So if you get it more or less, where's that? Okay, here. If you get that one more or less okay, then it is okay. But I'm using quite a lot of time for this, so let's get into spectral analysis shortly, because we want to go to foggy and those couple of samples for the samples from the group analysis. So let's go get that. So for the localizations, I think that you will get in the best results when you just increase the amount of two stations, like 2 or 3 at a time, and then see that how it's affecting on the original ones. Those original locations, they are, I don't think that you will ever get exactly the same, but if you are more or less there nearby, it depends on the grid, the size of the seismic network. In Pyhäsalmi mine, I think that if you get more or less 100 meters, I think that's okay, because the application and the usage of the S waves is different. So you should get more or less the same area. You don't have to be exactly the same. At some events, that's possible as well. Okay, let's go to spectral analysis. So it is this one, quickly through what we need. Waveform catalog. These are mostly the same that the localization has. Let's add this to the workspace and put it in the subset 2. This I'm putting that there. Then it moves it just below the localization. And you can see that it uses the velocity model network and the mini-sheet. I will take just that same signal that we had in the localization. The network, it is also the same file that we had Pyhäsalmi, and the velocity model is also the same. Right. This does want to have the event coordinates though, or for some reason, and we can use that same JSON file for that seismic event. And that's actually, we can see it from here, where the event is and what is its magnitude. So then we will go on. So what the spectral analysis does, as you remember from the last practical sessions, we need to now fix the phases of the P wave and the S wave. And let's start with the P wave. So the P wave is quite easy to recognize. Usually we have this very static background noise, and then the P wave is coming. So we just need to take that portion of the signal, what we think contains the first arrival, the P wave. Like that. And same time, we can also change this phase to S waves phase. And I think it starts somewhere over there. And I think it stops before the surface waves, this largest amplitude of the signal. Now that I look it might be that these are actually the surface waves over here, and this is the S wave. Especially in microsemi scale, it can be difficult to recognize them, but the P wave should be more or less easy to pick. Let's take another one, zooming all the signals here, amplifying a little bit to recognize first the phase of the P wave. I think it's that one, and the S wave, which I think it's that one. Yeah, these are the surface waves. This is portion of the S wave. It's difficult to pick the actual starting point of the S wave when the S wave returns. Arrives. It's probably here. But in this case, we just need the phase. And this actually only requires one station at minimum, but it uses this all as talked last time. So we'll just run it. Yeah, there's this. This needs to have at least 32 samples in this spectral level. This means that if we zoom a little bit, this needs to have 32 samples, and this doesn't have that many. So we need just to increase the amount of that. I think that the S wave does have that amount of samples already. I think this might be the same case. So there's this kind of minimum. So this can a little bit overlap. So I think now we should be okay. Yes. So it just needs to certain amount of samples to make the spectral analysis at minimum. So here we can see the two stations, the 16 and 21, the jet component that we picked for the P wave, and the signal is this one, and that is the fitting of the Snow algorithm. Let's not go into details on here. But from the fitting, it is possible to obtain the corner frequency, which is then used as the main parameter to solve some other parameters based on the P wave spectral information. And from there, we can have the source radius and the moment magnitude and slip and so on. And this actually says that this would be quite large event. It is large. It's 1. I think the original catalog says it's 1.2. So, and this is a little bit different. It's based on the seismic moment what we have derived from here. So this gives these kind of parameters based on these two stations and the peak of the P wave phase, and we have the same based on the S wave, which actually says that this is quite a little bit smaller by radius. The movement is not that large than in the P wave, and the moment is, I think the moment is a little bit.
So actually, how do we know that we make like the right selection in this spectral analysis? Like the form should have like similar trend to the linear function? Yeah,
this I think that the one way to look at is how coherent this corner frequency is, and this is based on the fitting of the Snow algorithm. So if you would take, let's say, if we change the S phase, something that is not right, let's say like that one, you would see that the spectral content is quite different. That was a P wave. I didn't change that, but if we look this one over here, so now we mainly have the surface waves, and we can see that the corner frequency is much larger, more high frequent than the original one. And I think the frequency is somewhere here. This is actually quite low for the, which one is, so it was this one, yes. Yeah, you can see that for this, the spectrum is not actually quite nice. It doesn't have too much of this kind of high frequency content that 21. I think it was 21. Yes. No, it was 16 where I misplaced it. Yes. So it's this one. So it actually does have much more of this high frequency content on these surface waves compared to this S wave phase. And the way it can be seen that if you have, let's say, taken one of these S wave phases wrong, you would see that the corner frequency is not that coherent. It may be that there's a lot of. So if we would take from all the other stations the right amount of S wave, so here is the P wave, and these are already the surface waves, and these are just the decaying amplitude. So the S wave is most probably somewhere here. But if we would take that one, we would see that as an off from this corner frequency that we had from the right place. Of course, if you don't know where the surface waves are starting and where the P wave phase is in the beginning, and then the S wave, and then the surface wave. This is the order of always, because those are the most slowest waves. So if you're not so sure, then you shouldn't pick the S wave. It's much more difficult. So if it's very hard to distinguish between the surface waves and the S wave, I would recommend not to pick that at all. You can do just fine with the S wave. You can do that since it actually uses just the P wave phase, and this is based on the S wave phase. So they are handled separately. And but the thing is that if you use both of those, you should have get not exactly the same parameters, but same-ish, so that they are more or less the similar levels. Like here, we have a quite large moment magnitude difference, but that is because we only use 2 stations, and there might be some error. That more the stations that use, the more coherent work results you would get. So this is how this application is actually using, and the solution is usually stable more stations that you're using, and you can have more confidence on the results. Okay. So I will quickly go through one thing, the last of those applications, these focal mechanisms, because this is something I'm most probably going to put in the exercise work. And I know that there's another application than Foci that you can kind of estimate the focal mechanism. So I'm more probably going to put that as well. They are working a little bit differently. The other one is based on the same thing as this Foci, which is based on the phase, whether the station first arrival is positive or negative. So it's kind of the dilatation of the waveform. And the other one is just strictly based on the single event and the spectrum. I will give you instructions in the exercise work though, so you will see that later. But let's go through the Foci, and I asked you to use the Foci in this USCB episode data, which you should already have in the workspace. And let's go through first one example event from that. So subject 2, let's go in the USB-C, and I already gathered most of the material here, what we need. So I have actually copied here the filtered catalog that only contains the magnitudes of 3.7 to 4.1. And we can use that in this. Actually, we can't use that. We need to have, we first need to have a signal, of course. And I will just take one from here. I take that 5, for instance, and I know that this has the seed signal, but we can run it from all. It just takes those that are available. It actually had more of those. Oh yeah, it has different kind of stations. So let's take those 2 away and just take the seed signal, right, like that. Yeah. So this one has different networks, so it takes those, but we only need this seed signal on that one. And the seed signal, it cannot be used in the focal mechanism Foci application. It needs to be this mini seed. Again, we will need to transform it to seed to mini seed, and we have it here now. And that one can be used in this Foci. And again, this wants to have the network inventory. That was. And then the ray tracing angles, which is needed for this application. All right. And this software takes this for granted, this I think the JIT component only, we do have another component as well, but it's only access the jet component. And you can see that for this one, we actually need to pick at least 8 stations. And what we are picking here in the focal mechanism and this way, something we need to have this. We need to find out what is the first motion of the seismic signal. And again, we are taking the phase of the P wave. And I think that is the first arrival. I think that I need to pick that first before I can explain you why this is so. I know that you have gone through that in the lectures, though. At least Elena told me. So the next one is slightly more difficult. I would say that is the P wave. So we need to take the phase, what is containing the P wave. And this time I don't think that this has the limitation of the sampling. That actually is quite interesting. So you can see that there is a microscale noise or events, and this is the actual event over here. So let's see which one is the real one. I would say that these are the micro tremors here, but they are not associated to the actual seismic event that we are picking. But that is the first P wave. So let's take that one. So we need to get the peak of the P wave and it's ending here. So it kind of looks at which way the first arrival is moving. And it's more probably taking this one over here. So it's a semi-automatic application. Okay, this is more clear. That one is the P wave starting from here. So we need to kind of isolate the first motion. I would say that it's that one. And a few more. Okay, this is a tricky one. I would say it is this one, but it can be also that one. It kind of doesn't matter because they are on the same at the same size. That's down. Another one, you should always zoom in to get a view of the first arrival. And we have now 7, we need 8. And again, zoom in. That's more clear. All right, now we have all those phases picked. And again, this wants to have the event coordinates, mainly for the mapping. It's finds from the signal download tool and taking the JSON file. It just shows the location, and then there's not too much of a parameters on this one. It's just the density, and we are usually using this 2,700 kilograms per cubic meter, which is the average density of the crust. And then we can have different kind of solutions, very basic double couple, multi-null solution, and then full solution, which calculates whole moment tensor based on these peaks. And then we just run. And as an input, Out of bound. I think that it just wants to have little more. These are always very clear, these errors on this platform. I would say that this is because there's not enough samples, though it didn't say it. That one looks a little tight already. Right, let's see. Did that work out? I've never had this kind of error message. It's still saying the same thing. Well, isn't this a nuisance? This really shouldn't. It's just kind of taking the largest amplitude of that phase. It takes the null phase. Well, that is odd. Well, if we look just, I have made this one example before, so we can just look that one. But now that how this is working, it's working that it looks the largest amplitude, whether it is negative or positive, it takes it as a peak. Then it looks where the 0 point is over here. And it kind of makes this triangle, just saying it gets the amplitude and as well the direction that it's negative or positive. When we are measuring from the surface, you remember that the dilatation of the observation is depending which way the ground is moving. And when we are having an earthquake, let's say that one, when these are moving, this is in the macroseismic example, but if we have this kind of shear or strike slip focal mechanism, it means that the other plate is moving on the, let's say, north, and the other one is led south, which means that if we have stations on these sectors, in this sector, we would have the pull that the material is actually pulling away from the sensor. But if it's on this region over here, it means that it's coming towards the stations and vice versa. And this can be seen as that, as this interseismic signal. Let's go look the working solution what I made. Where did I put that? No, wasn't there. I need to find one cookie for you. See. kind of have that. Okay. Well, this one, this is older one, but I think it's valid though. It's missing something. Okay. I should have the, you know what, I'm just going one another place to look at. Maybe I will just take it from here too. This is more the unknowing thing that we don't have any search option in this work-based tree, which can be in this kind of situation would be quite good. Okay, I should have this one. All right, let's just take that one. It's missing things, but I've someday done something. So as said, that will produce 3 different focal mechanism solutions: the double couple, deviatoric, and this full solution. And if we look this double couple first, we would have something like this coming up as a graphical way. So in this output, we have this red cross over here, which is the center of the epicenter of the seismic event or the earthquake. And the stations over here are marked as relative locations comparing to this event. So, and usually these are that the north is north and south is south. So they are in the right geographical locations. And now the black or whites are the defined first motion of the seismic in the seismic observation. So this white one, if I now remember correctly, it is that it's actually moving away from the seismic event, and black one is that it's actually pushing towards, if I remember correctly now. So each of the stations are picked for this phase, and the soft application is based on that phase pick, determining whether it is up or down. So is it pulling or is it tracking towards pulling towards the seismic event or away from it? And then the basic, based on this, this application will determine the appropriate focal mechanism. And in this case, we actually have a quite clear, well, not clear, but we can have some traits of the shear mechanism, which would be in these examples over here, similar to this. But since it doesn't have exactly like that, it looks more like this. So there is movement on this way, but also movement apart and in the vertical motion like this one and that one. And as you know that usually the seismic events are happening in the one zones, that it's moving, let's say that this plate is on that way, moving on that way, and the other one is moving on the opposite direction. but we can't know in mathematically which one is the correct way. We don't have to know some information about the geology itself, which one is the right one, because this is just doing this. This is just doing it in the mathematical solution way, and to explain this, we can look that one. So in this case, we can see that the fault plane is in this direction. But when we are modeling this focal sphere, we can see that there is this primary axis, that is the correct one. But in purely mathematical way, this is also true. So this could be opposite direction. So if we just look that one, we couldn't see that which one is the correct one. We need more information on that, like geology. But what we can know from that one is that whether the mechanism is this kind of shear, or is it a normal extension, or is it a reverse thrust, which means that how the plate relative motion is done. Also here and here. So it means that this can tell us quite a lot about the actual movement, even though it doesn't automatically tell that which one is the correct one. But if we would make more of these kind of, let's say that there's a lot of seismic events, we would see the direction, the right direction, when we see that where the seismic events are location. And this is already going in the group analysis. Yeah, it was a shame that we had that error in that. Focal mechanism. We could actually make a fast one for another event. So we need to take another signal. Let's take now, let's take that one, 3.7. Run it. Then we need to change that to mini seed. Always remember to run these things. Now we have the new signal, and we just change that over there. This actually has 10 seismograms. That means that there's 10 stations that have observed this focal mechanism, which is good because the minimum is 8, but more we have, the better. We need to take the correct event file, this JSON. That was still the old one because I'm using the same application. So let's go and look another time. Okay. That one.
Because, well, and then I was doing the exercise with you, and I was not able to run it because it said that I only had 7 seismograms. That was the reason that we couldn't like run it.
Yeah, it's demands the 8 one. So yeah, so one option is always to look the seismogram before using the application. That does it have enough of seismograms? Yeah, and I think that of course if you put more of this components over here, but it doesn't make any sense because they are still at the same location. So it might let you do it, but it's not that good. Okay, it seems that I know that it might be that for the exercise work, I'm actually picking part of this is now doing this because it kind of has the before seismogram still active, because this is the same application. Maybe I will take at least one of the events that will work for sure. This should be now working. Yes. Right. I think this one still has that picking, even though we haven't picked those. It's that one still got it. But we don't have to pick it. We already have that. And let's try again. Okay, now it works. Nice. Can't say what was the problem previously. But now let's first see this double couple solution, which looks something like that one. So as you can see that there's actually most of these events has only this compressional wave. So it means that it's actually going towards the seismic event, and in this particular one, this kind of solution is coming from this very simple one. But let's look for the full solution, which means that it actually is trying to get the moment tensor out of from those amplitude, what it's calculating from the phase peak. And still it says that it looks something like that. So it's more or less pure. It has a little bit of this tensor component. And if we look at it like that, it looks more like this normal extension. Sorry, it does have, of course, this shear part of the movement is shear, and part of it is the normal extension. Something like that. I would say that it's more that than it's more this transpression. It's more transtension. But this wasn't a very good example, but of course you never know what kind of focal mechanism you will get. So I will look some more better for you for the exercise work and let you pick one and use that against that that one I have picked for you. But if we look still those seismogram peaks over here, I would say that there's no problem with the peaks themselves. So the usability of this application is just that you will recognize the first arrival B wave, and just isolated with this phase peak. It can be quite compact, or it can be larger like that, but you can't take those these ones over here because they are already, they may be in a different wave, for example that one. So I think that the most easiest is just to zoom in the very beginning of the trace and try to find the first clear P wave motion, and in this case it is that one. In the Pyhäsalmi mine, for instance, there are some stations that have quite large errors in the noise in the system itself, so sometimes it's very difficult to pick. But in this case, this is quite clear. So the system will be picking that one as the main amplitude, and then it makes some sort of triangle here and calculate the moment from that for this full solution. You can read more on the application guide. But this is how it is going to be isolated.
And yeah, from the file that we obtained, we should check the big block you said and the full one. Those two are like the main ones.
These are all a little bit different. The double couple is the most simple one. It's just trying to model the mechanics using just the two kind of perpendicular force axes. And the full tensor, it actually demands this 8. I think is it this? If we take no, it demands still. The full solution is the one that demands at least these 8 stations because it needs to have all the components of the movement in different places. But yeah, but run them all, and the results should be more or less the same. They should not be too much of difference between them. Of course, that can be sometimes happening because this double couple is it actually is very simple way to model the mechanism because it's just used these two kind of power axes. But the full and the deviatoric, they are kind of give more information if there is like multi-component movement. It's not just a pure normal fault or reverse fault or just a shear faulting or strike slip. It kind of gives information on the other movement as well and has more statistics on that.
So preferably we should like focus the analysis on the full.
You can just, I think you can look them all. I'm most probably going to ask you to put the images of all 3 of those. There's also this, I think it's this ask file in the on the output that actually gives some parameters, but I think we are going to focus on the images as one. So I'm going to ask you to put all of the 3 ones, the double couple, deviatoric, and the full one in the Excel work, and to see is there any different, and if they are more or less the same, you can pick one and say that what do you see from that, or is it possible to see anything?